thank you for the opportunity to talk here, and for everyone to stick to the very last moment of the conference. I changed a little bit well, didn't change the title, but I made it a bit more emphasis of the project we are developing at Swansea University. So I joined Swansea University a couple of years ago, also with the pandemic. So that has been a bit awkward how to develop both experimental things we want to do there, as well as the computational a bit better, but we also needed to find people. So basically, among the different projects that we are doing in the group, we are very interested in modeling biocrude oils and modeling asphalt, and that's why I added and emphasized it also. We are working on asphalt. And the piece on high-throughput generation of chemical isomers is something that we were also very lucky to get one scholarship for a student last summer from the network, and she was working actually on that seed that we hope is going to be something that is going to grow and develop further into the research that we want to do on that. So first, let me introduce quickly, in case I run out of time at the end, with the acknowledgments. This is a work mostly done by Dan York and Anna Catton, who was the student with the scholarship last summer, and Dan, who is doing a master with us, and then also with some of the people collaborating from the group. It builds also on some project I was working in the past at MIT, where I was for 6 years before joining Swansea, and I still keep some collaboration with people there. And then we also have very nice collaborations with Chile, with the University of Bio Bio, where they do the actual experimental characterization of the biocrude oils and the asphalt, and then with some people as well in Taiwan, where they are helping us with the piece on machine learning and graph neural networks. So basically, I mean, the main goal of the things, or all the projects we try to do in the group, is connected to something we discussed also yesterday about the fact that we are in a world with limited resources, and we have increasing global population. That imposes, let's say, many challenges, but also generates a lot of waste that we believe could be also an opportunity to try to produce some of those materials out of that waste. So basically, what everything we do, both experimental and computational, and also through many collaborations, is trying to connect these two things. How can we produce and design functional materials for different applications, but coming out of waste resources? And basically, the idea is look at what the different waste resources we have out there, mostly biomass, bring, identify those building blocks, and use those sustainable sources to, let's say, combine them to build and study how to assemble that into materials. And now study as well how is the deconstruction of those materials. And this is the core idea of what we do. And then, of course, from that, we focus on certain applications. The one I'm going to talk about today is those bio-based asphalt, or how to do these biocrude oils is a sort of bitumen to make asphalt more durable and, let's say, displace the source of fossil fuels. And then we use different techniques of multi-scale modeling to study these sort of materials. So in the experimental part, we are working with different sources of biomass, mostly trying to understand how the different components decompose at high temperature and high pressures into these carbon materials. And then we create models that help us to understand how those materials are. And when it comes to the biocrude oils, it's very closely connected to modeling asphalt. And this is a very challenging problem because no one knows what is in there. So there are so many organic molecules all together that it's very difficult to characterize. And it's also difficult to characterize because of such a complexity in the amount of organic molecules, but also because of the difficulties analyzing that. I mean, every time you talk to some experimentalist or anyone in materials characterization, and you ask them that you want to do some sort of I don't know, AFM, or you want to do whatever experiment it is, no one wants to put that sticky black bitumen into any kind of lab, right? So that makes it very fundamentally challenged. So there are, however, a way that based on solubility differences, people characterize the molecules into 4 types: saturates, asphaltenes, resins, and aromatics. And being the asphaltenes, the key ones are polyaromatic hydrocarbons that they cluster and form some sort of nanoaggregates, that they are like in a kind of sea of resins and the other components. So what people doing in terms of modeling is to come with some kind of average description of those 4 different types. Now, what we want to do is within those sort of models, how can we understand how asphalt ages and how it cracks? So basically, everything happens initially because of the oxidation of the molecules in there. When these molecules oxidize, and maybe in this is a bit more clear, they increase the amount of those asphaltene clusters. And that's is a process of hardening of the material that leads then to the cracks. So what we want to understand in collaboration with the people in Chile is how can we add then some rejuvenators that bring that properties back, closes those cracks, but also doesn't compromise the performance of the road under working conditions. So basically, at the end of the day, from our point of view, is how can we then study the design of certain rejuvenators that contribute to mitigate that aging. So we need to understand how is the reactivity, how is the oxidation mechanisms of asphalt, as well as the biocrude oils that we want to add to those asphalt materials. Now again, where to start? This is an example of one of the most complete characterizations that has been published about biocrude oils. These are biocrude oil coming from algae. As you can see, there are many different types of molecules there, and the asphaltene-like matter is what you see in black. And there is still one piece that no one knows what is in there, but at least, and this is the most complete one. In many cases, the available data is even shorter, and mostly because you need some kind of pyrolysis MS technique to be able to volatilize all the very heavy components. So there is much more data on the light components of the biocrude oil, not that much on the heavy fraction. But in any case, we, based on that data, we developed some molecular models which basically, based on what we see in the analysis and based on what we see in the literature, we propose that on average, for instance, in this case, those molecules that you see represent more or less what would be in the mixture. But of course, could be many others similar to that. So then is when we came with the summer project we have last summer, in which basically we say, okay, if we take a different source of biomass and the available chemical characterization, and this is just an example of 9 molecules, but there were many more. We take those that has been observed there, and then we generate, and this is the very nice cartoon we got last summer, we generate then, feed those into an algorithm that generates all possible isomers out of those molecules, and do that for any sort of molecule that has been ever seen or characterized in this sort of materials. Then we do different analysis of that. I'm not going to get into details. We can discuss this later. But basically, we do different DFT calculations on that. We calculate different reactivity descriptors of that. This is just one example of them. So we calculate where nucleophilic or electrophilic reactions would take place. We integrate those areas into partitioning of the electron density, and then we come with certain specific numbers is the reactivity of those atoms within that molecule. And then we put all that together to kind of generate the data that we need to do then the different simulations or to train the graph neural networks we want to train. So basically, just as a summary, we get any molecule we find in biocrude oils derived from biomass, get these initial molecules we found with the isomer generator, generate any others that could happen, because of course, if they are similar, probably are there, but they were not observed. I mean, tiny differences could be missed in this kind of characterization. Do calculations on all the properties on the electronic structure of them. This is something we have done already. And then we use this for two things. We use those models to run molecular dynamic simulations and then be able to look at how these clustering mechanisms happen, and also use it to train, this is what we are doing with people in Taiwan, these graph neural networks for two things. One is to actually see if we can predict the properties without the need of the DFT calculations. The other one is also to help assist in the molecular dynamic simulations, which is also very challenging in these materials, by trying to get better force fields for this sort of simulation. So this is overall kind of a schematic idea of what we are doing in the field of biocrude oils and asphalt. And with that, I thank you all for your attention. Thank you.